Okay, welcome back to Legion School, everyone. So today, I'm going to continue talking just a little bit about some of the stuff that we talked about last time, which is we're going to look at some of the different uh, things that were going on in the creation of both index-based trees and region trees. In particular, something actually was optimized since the last time that we looked at it, and I actually want to show you the change because I think you'll find it very instructive. A little bit later, then what I want to do is actually dig into some of the details of how field spaces work and how we allocate fields and some of the internal data structures that we use for tracking which fields are allocated in a particular field space and how we represent field spaces internally inside the runtime. And then once we've done that, meeting today, we'll actually start digging into the logical dependence analysis. And if not, we'll start doing that the next time that we meet. Okay, so let's actually start off with the thing that we changed since the last time. I actually just did a push to the public repository about 10 minutes ago to actually make this change publicly visible so we can show everyone this. So you'll recall that the last time, one of the things that we were looking at, if I jump down here to regiontree.h, one of the things that you'll see that we were looking at were how we track the logical and physical states on individual region tree objects. So if I go to class region tree node, what you'll notice is that we had these data structures down here. Let me scroll down and find them. We had these data structures for tracking. Actually, they went too far. That was region tree node. Let's see, where was it? I'm missing the state objects here. Here we go. You remember that we had these logical and physical state objects that we were tracking on individual region tree nodes. So every single region tree node had a data structure that would track all of the logical and physical states that could be indexed by the various contexts that were created as part of the high-level runtime context instantiation. And what you'll see that we have now is, or if you remember, last week we were storing these objects inside of what we were calling Legion stacks, which are just some data structures that had a fixed size that allowed us to have a fixed number of logical states and to do dynamic allocation up to so that maximum number of states. And what I've done since then is I've actually gone through and replaced those Legion stack things, which was actually, for two reasons. One was that we found that there was a memory savings by actually having a more dynamic approach for storing these state objects. And the other reason is that it's kind of unfortunate we had to have a maximum number of contexts in our Legion config file that would, specify the maximum number of contexts that could be allocated on any particular Legion node inside of the runtime. And so what we've done is we've actually adapted this dynamic data table or dynamic table data structure that the low-level runtime actually uses for tracking things like events and reservations, which I think Sean went through in a previous lecture. And now we're using it to store these logical and physical state objects that we've actually for every single region tree node. And what this means is that we can actually have a way of dynamically indexing into these data structures and allocating new entries whenever they're needed. Let me show you where these dynamic tables are declared and defined in the high-level runtime. And you'll see that they'll look very similar to the low-level runtime implementation, so I'm not going to dig into detail. I will mention the one major difference that we have. So we have this file in the high-level runtime called Legion Utilities.h, and it contains a bunch of different objects that are sort of used all over various parts of the high-level runtime. They're not tied to any particular pieces of the runtime, but they sort of act as general utilities that we use in lots of different places. So one of them, of course, here that we should expect to find here is this dynamic table class that we were just looking at. You'll notice that this looks a lot like the dynamic table class from the low. It has a bunch of, or effectively has a root that points to the base of the tree, and then we have two different types of nodes inside of the trees that we're tracking. One is going to be a base type, and one is going to be an intermediate node type, and one is going to be a leaf node type. If I actually scroll up here, you can actually see those two different kinds. The dynamic table node base is one of the intermediate nodes, and then one of the leaf nodes will be one of the types of whatever the thing we're storing, whatever this type, this element type is that's declared on these various allocators. And you notice the allocators are templated on these element types. And so those are just the logical states and the physical states in the case of the way we're using it in the high-level runtime. So I'm not going to go into a lot of detail as to how this dynamic tree works. I will say that what it does is it works exactly the same as the low-level versions that Sean talked about earlier. Effectively, you start off with one intermediate node at the base, and it can store up to n entries of the leaf type nodes. And then whenever you need to add to it, you just keep adding levels to the tree above it and filling out the rest of the tree. The one difference with the low-level runtime implementation and the high-level runtime implementation is that at the very base of these nodes, it used to be that if you looked at these, let's see, this dynamic table node base, when you looked at this, the set of elements, the base nodes in the low-level runtime implementation were just, an array of the actual elements themselves, whereas here in the high-level runtime, we're actually storing pointers. And this allows us to dynamically allocate the leaves as necessary without having to actually allocate storage for all of the leaf entries right away, which will actually save us some space in the long run. So that's primarily the only difference between the high-level and the low-level versions of these dynamic tables. Let me actually show you, while we're here, some of the other objects that exist inside of this Legion Utilities file, because we're actually going to encounter some more of them a little bit later today. Let me scroll up here a little bit. It's actually through some of the objects in here. We've actually seen one of these objects before. We've talked about it before. So we have a structure here for tracking region usage, which is effectively just tracking privileges and coherence and reductions on a particular region. You'll see that we'll use some of these region usage objects when we go to do traversals of the high-level in the high-level runtime region trees for actually doing dependence analysis. You'll actually see that we have most of the dependence checks functions for checking for independence of privileges and stuff in here. In particular, this check dependence type is going to prove to be a very important function. You'll see that we've made it, a static inline function that we can put in pretty much anywhere inside the runtime. And apparently, my Mac is reminding me that I have an update, so we're going to skip that. Okay, so this dependence check function, we'll see this get used in a bunch of different places. Here's the thing that we've actually seen before. We've talked about these auto lock objects that we use for doing most of our locking inside the high-level runtime and the low runtime as well. So these auto locks are just objects that allow us to take a reservation when they're declared and then release it once the auto lock is destructed. We've looked at those before. We have these serializer and deserializer objects. Here's the deserializer. And we're going to see that what these objects do is help us to build buffers of data that we are going to use when serializing data structures to send them between different nodes inside the Legion runtime. So these serializers are going to be used for packing things up, and then deserializers are used for providing a similar interface for unpacking things. And we'll give some examples of how those are used probably in another lecture. We have some checkers for doing our deserialization and so forth. The next important class that we have here is this Bitmask class. And this is what we're actually going to see get used a bunch today. And actually, we're going to talk in some details about how we use these Bitmask classes. But effectively, what we have here is we have a isolated class that allows us to store a bitmask. It allows us to store a bitmask of up to max number of bits. And the idea of this bitmask class is we wanted to sort of represent, it's a way of representing a set of indices. And so we'll assume that, if a bit has been set, that the index for that bit is contained within the set. And what this allows us to do is actually we can define a whole bunch of operators on these bitmasks to do all sorts of interesting things. So, for example, we can take the complement of a bitmask, we can OR a bitmask with another bitmask, we can AND them to take the intersection, we can take the XOR of them. We also have similar operators for doing direct assignment directly into these bitmasks. And we also have, important ones for things like testing the disjointness between two bitmasks, whether or not they're overlapping or not. So that's what this star operator is. For anyone that's looked at separation logic, you'll know where that star operator comes from. We also have ways of doing set differences between bitmasks, so we can have a subtraction operator. We also have a bang operator to test whether or not the bitmask is empty or not. We can also do things like shifting and so forth on our bitmasks to shift bits left and right. Okay, so we have these bitmask class, and we're actually going to use them for storing these sets of indices that have been set, and we're going to see how we're going to use these bitmasks to store sets of fields that are allocated as part of region usage later today. The other thing I'll mention is that we actually have a whole bunch of different flavors of this bitmask, all of which have the same interface. So in particular, let me talk about some of the other flavors of these bitmasks that we have, just so you can be aware that they exist, and I'll show you where they actually get used. So we have a variation on the bitmask interface called two-level bitmask. It has the exact same interface as the base bitmask class. The main difference is that this bitmask, so you'll notice this first bitmask that we looked at only had just a vector of some kind of type. Usually it's a UN64, just a bunch of bits. And we have just an allocation of all of the bits inside of our bit vector. The two-level bitmask has the same interface, but it has an extra, in addition to having just the vector of all of the bits, it has an extra summary mask, which is used to track if a bit has been set in an index in any one of these different entries of type T inside of our internal bit vector. And what we're going to use this for is the summary mask actually makes a bunch of tests, such as the intersection test and the disjointness test and the empty test, much more efficient, because instead of having to iterate over this actual array, we can actually look at the summary mask and determine things a priori right away, whether or not all of the bits have been set, or whether there's a possibility for intersection we actually have to do the long test or not. And so these summary masks actually do make a difference for very large bit masks, and we do tend to use very large bit masks inside of Legion, especially when our applications tend to allocate, field spaces that have up to 2,000 or 4,000 fields. These bit masks are actually going to get fairly large, in which case these summary masks actually end up making a big difference. We have some other flavors of bitmasks that again implement the same interface. Here's one that if your processor has SSE, we have a SSE bitmask, which is just going to make use of SSE vector types for doing a lot of these operations. So you can see the internal representation is a type union here of bits, depending on whether you're looking at the bit vector or the SSE vector. They're all doing the same thing. We also have a two-level version of the SSE bitmask for actually doing the same kind of summary mask trick, but with SSE vectors. And then we also have versions for AVX as well. So if your processor has AVX, have an AVX version of this bitmask that has all the same operations. And then we have a two-level AVX bitmask also for doing very large bitmasks. Okay, let me actually show you an example of where these bitmasks are going to get used. So if I jump back to, let's actually go look at, I believe it is Legion types.h, and we'll see a declaration where we actually use some of these bitmasks. Search here. Okay, so here's some examples of cases where we've actually used these bitmask types that I've been talking about. So one of the examples, so we actually have a bunch of logic that helps to pick the right version of these bitmasks, depending on, say, for example, the maximum number of fields that Legion users have configured the runtime to use. So just for example, actually let me jump back here and show you in Legion config.h, one of the things that the user can specify when they compile the runtime is this max fields value, which says what are the maximum number of fields that can be allocated inside of any particular field space inside of the high-level runtime. And our default value is 512, but we have applications like S3 that use much bigger field masks or bigger field spaces, often needing up to 2,000 or 4,000 fields inside of a field mask. And so we have to configure this max fields variable macro properly. Okay, the runtime then has a bunch of logic based on this max fields macro to actually figure out which of those different bitmask flavors to use. So if I jump back here to, let's see, we were in Legion types.h. So if I jump back to Legion types.h, I search for, here we go, max fields. What you'll see here is some logic that helps us pick the right version of this of the bitmask to use for declaring this field mask type, which is you're going to see how you're going to use these today. But effectively, a field mask is storing which fields are active inside of a field space at a certain point in time. Effectively, what we need is just our bitmask to be as big enough to store one entry for each of the different fields inside of our potential field space. So you can see we have first, if you have AVX in your processor, if we have a field space that's bigger than 256 fields, then we're going to use the AVX 2-level bitmask here. Otherwise, if you're not bigger than 256, then we just want to use the normal AVX bitmask. But if you're not as big as 128, or if you're not at least 256 bits, then we're only going to want 128, so we can use the SSE bitmask. And if you're not bigger than 64, then we're just going to want to use the normal bitmask, which is a base 64-bit entry. And then, of course, if you don't have AVX, we have a separate chain for picking out the right field mask to use if you only have SSE available. So in this case, you can either use the SSE TLB bitmask if you have more than 128 fields. If you have more than 64, we'll just use the base bitmask. And if you have 64 or less, we'll just use the standard one. And of course, we have similar things for if you don't have AVX or SSE. And so the runtime will go through and pick out the right flavor of these bitmasks to assign to these to be this field mask type, depending on what you set your configuration to and what kind of machine that you're actually running on. Let's see. And this one important detail about this is that all of these different flavors of these bitmasks all implement the same interface. So this is important because it means that this field mask will always have the same interface that we can use throughout the rest of the runtime, which we'll actually use for when we so wherever we use these field masks, effectively we've got a level of indirection here that we can change around with the implementation type of field masks, but the interface will always be the same. Okay. I'll also comment here that we have a bunch of other kinds of masks that exist here for specifying things like node masks or which are tracking sets of nodes and so forth. And this will actually allow us to track sets of nodes that we've sent things to. We use these bitmasks for tracking node masks, and we also use them for tracking things like processor masks and so forth. So there's lots of places that we use these bitmasks for doing various different kinds or for storing different kinds of sets of things. And we just use them copiously because they're a very nice interface for using. Okay, let's actually move on now to actually talk a little bit about how field spaces work, and we'll actually see how we make some of these field masks so you can get a feel for what actually goes on inside of allocating, or how we actually create some of these field masks and how we're actually going to end up using them. So let's jump back here. I'm going to jump back into region tree .h just for a moment, just so we can look at the declaration of field masks, field spaces, and we'll see how we can actually go through and allocate fields inside of field spaces, and we'll see how those get used to make field masks. For field space node here, which is our internal representation of a field space that gets created by an application, by a Legion application. So we looked before at the create field space call, and we know that it goes through the create node function, which is pretty standard. The field space nodes are actually much simpler to make because they don't have any parents or children or anything like that. They're just sort of one-off things based on when the application invokes them. And the important thing that field spaces allow you to do once they've been made is they actually allow you to allocate these inside of the high-level runtime. And so what we're going to do, what I think I actually want to do is actually to trace through allocation of a field ID through from an application level, from the interface, the Legion interface, back through to how it comes to these field space node objects. And eventually what we're going to see is we're going to end up calling one of these allocate field objects to actually allocate the field inside of one of these field space objects. Let's actually trace through and see how that happens. And we'll see how we update the data structures inside these field space nodes. Okay, so if I go to legion.h, which is our interface, I search for field allocator. There are ways to get field allocator objects from the high-level runtime. At some point, an application will probably use a field allocator to allocate a field on a particular field space. So they call allocate field. We search for allocate field. We can see it's actually an inline method on this field allocator object. And really what it does is that just turns around and calls the runtime, asking it to allocate a field for this particular field space. It gives the size of the field and the desired field ID if the application has specified a particular field ID to use. It also says whether or not this is a local field allocation. Local field allocations are fields which are local only to one particular task context. They can't escape that particular task context. But by default, these are false. So if we jump into runtime.cc, let me go back here and move into runtime.cc. We'll see where this allocate field call comes into the runtime. Okay, here's our call to allocate field. One of the first things we're going to do, there's some debugging checks here for doing basic checking. But the first thing we're going to do is the application actually asks us to pick a field ID for it that's unique within this space. What we do is we actually call this getUnique field ID to allocate a new field ID. You'll recall that this is a special one of those methods that we talked about before that calls getUnique on something, and what it's doing is effectively every runtime has its own offset. They're all stepping through space by the number of different nodes in your system, and so that guarantees us a unique field ID that's globally unique across the entire system. Once we've got that, what we can do is actually ask. We'll ignore the local case for now. But what we'll do is we'll actually ask our runtime region tree farce to actually allocate this field on the particular field space. So we're going to call this allocate field method. We're going to pass in the field space, which we're going to be doing the allocation on, the field size for the field that's being allocated, the new field ID, either the one that the runtime or the application gave us, or the one that the runtime selected as being a new unique field ID, and a pointer and saying whether or not it's local or not. So let's jump back into region tree.cc. We'll see where this allocate field call comes in. Actually, I wanted region tree.cc, sorry. Here we go. Okay, searching for allocate field. Okay, here's our call to allocate field, and you see we're getting in all of our parameters. The first thing we're going to do is we're going to get our field space node for this particular field space. This is where we pull our node out of the existing set of nodes. If this is a local field, we can do some special checks, but if it's not, what we're going to do is we're just going to do the default case and call allocate field and pass in the field ID that we want to allocate, the field size, and whether or not it is local or not to the field space node. So if we continue searching for allocate field here, we should actually let's see. Okay, field space node, allocate node, or allocate field. Okay, so what you see here is that we've got a new field ID, and we've got a size and a Boolean saying whether or not this is a local field or not. First thing that we're going to do is we're going to grab the lock on this field space object so we can mutate some of its internal data structures. And the first thing that we're going to do is probably the most important thing that we're going to do for this allocation of this field ID, which is we're going to pick an index inside of this field space in which to allocate this particular field. And so what does it mean when I say pick an index? Well, the way that we're going to represent field spaces are with these field space or field masks objects that we looked at earlier, which are effectively just bitmasks. And so what we need to do is we need to pick an index inside of these bitmasks in which this field ID is going to be assigned. So effectively, there's a level of indirection here between mapping from the field IDs that get allocated on a field space object to the actual placement inside of these bitmasks inside that we're going to use to represent, which fields are active inside of a field space as we're doing traversals on the region tree. And so what we need to do is pick an index in this field mask, which is yet to be assigned on this local node, in order to say that we will map anytime this field with this field ID here is active, the bit in the corresponding location, index location, will be set inside of that bit mask. So what we do is we call it allocate index. I'll tell you, we'll go look at this method in just a minute to actually show you what it does. But what this does is it returns an index in which to associate with this particular field ID. So whenever we see this field ID, we know we should set the bit inside of the field mask at this particular index. And so we allocate this index, and then what we do is we keep a map. This field's data structure here is a map from field ID to what we call the field info. And this field info stores all of the metadata associated with this particular field inside of this field space object. And in particular, it stores three things. It stores the size of the field, it stores the index that it should be allocated outside of the bit mask, and then it stores the whether or not this is a local field or not. And then there's some updates here in which we have, if we're doing parallel field space allocation, we should be sending updates to other field space objects so they know about the existence of certain fields. But in the most part, this is the most important thing right here, is storing this in this field's data structure, the information about this newly allocated field, including the index in which it has been allocated. So let's actually go look at this allocate index method. Okay, so this allocate index method is pretty simple. It takes, Boolean saying whether or not this is a local field or not. It also takes an optional goal index. In some cases, what we want to do is actually, if, for example, another node has actually allocated, actually, I should say that one of the important details of the high-level runtime is that these field space objects are actually allowed to have different mappings for the same set of fields to different indices across the runtime. And what this allows us to do is to actually do parallel allocation of fields without having to communicate with each other synchronously. So nodes can go ahead and allocate fields in whatever indexes they want. And then what they do is they communicate to each other their particular mappings whenever they need to send field spaces between different, or field masks between different nodes. And we're going to see there's a mechanism for doing a translation, effectively a permutation of a field mask whenever it gets moved between any two nodes inside the system. And so what this goal is doing is actually, in order to avoid doing the permutation operation whenever we move field masks between nodes, we actually want to try and keep the same mapping from field IDs to indexes across multiple nodes. Whenever nodes get an announce statement, they can actually try to allocate a field at the same index that it was allocated on the original node. And so that's why we have this optional setting here is to try and maintain that parameter. But if goal doesn't exist, then we're just going to go ahead and do our normal allocation and try and find an open index space or an open index inside of the field mask in which to allocate this particular field. Okay, there's a little assumption here that we're already holding the lock. We know that's true from the place where we saw allocate field or allocate index called before. We know we're already holding the lock. If there's a goal index, what we're going to do is check to see if it's already in the set. If our set of allocate indexes, this is actually a field mask, which tracks which indexes have already been set. So we first check to see if if the bit has been set at the particular index that our goal is at. If it hasn't, then we can go ahead and claim it and add it to our set. Let me actually just show you where this. Let me show you where this allocate indexes is, just so you can see that this is a field mask and what it looks like when it's declared, and then we'll come back here and look at the rest of this implementation. So if I jump back to regiontree.h, we search for class field space node. What we'll see here is this is our field space object. Down here at the bottom, we have most of our data structures. What you'll see here is that here's our field mask of allocate indexes that we were just looking at. So you can see this is a field mask that was one of the things that we saw declared earlier today. And these allocate indexes are just tracking which indexes have already been allocated to particular fields. So if they're set to 1, they've already been allocated. If they're still 0, then they haven't been allocated. And also here you see this other data structure I was mentioning earlier, which is the set of field info objects, which is just a map from field ID to these field info objects And of course, these field info objects, I believe, are declared. Let's see. Here they are. Here's the field info object. You can see it just has some basic information like the field size, the index in which it's been allocated, whether it's been local, whether it's been destroyed, so forth. Just some basic information about the field that we can keep track of. Okay, let's jump back and look some more at that allocate index method. Dig into it some more for allocate index. Okay, so we have this allocate index as field mask, and we can check to see if the bit has been set for our goal. If we had a goal index, if it hasn't, then we can claim it and we're done. Otherwise, we have two cases here for handling the allocation of fields into particular field indexes. And so what you see is the first case here is the case where the total number of runtime objects that we have is actually less than the maximum number of fields. And what we do here is we actually, to help with the parallel field space allocation, the idea here is that we effectively have different stripes of indexes corresponding to different runtime objects, which allows these runtime objects to try to do static partitioning of the field space so that they can do dynamic allocation in parallel across multiple runtime objects. And so what we do is we first try to allocate on our stripe or on our strip, and if our strip is full, then we go on to the next runtime from ours and continue walking through until we find an index that has not been set. So you can see this is all documented in the comments. I'm not going to go through this code in detail. It's kind of just nasty integer math. But really what we're doing is we're trying to allow parallel field allocation in such a way that we can make sure that we get the same mapping from field IDs to indexes across multiple different nodes inside of the system. There's also an else case here, which we actually happened across last week, which is that we can actually have a case where we have more runtime objects, Legion runtime objects, than we do have actual fields inside of our field masks. And if this is the case, then effectively there are a bunch of nodes which can't even get a single static partitioning, a single index in a static partitioning of this field mask. Instead is we just pick a random allocation integer in which to start trying to allocate from on a particular node based on the maximum number of fields. So we generate this random integer and then mod it max number of fields, and that gives us our next allocation index, which we're going to try. And then we can iterate through linearly and try to find the next available index starting from that particular location. And this will wrap around the indexes until we find one that it works. And of course, one thing that can always happen in this allocate index method is that if we actually make it down here out of this if-else branch, it's always possible that we've actually allocated however many the maximum number of fields are inside of our field space. So if you try to exceed that maximum number of field allocations, we actually need to give you a nice error message here saying that you've exceeded the maximum number of allocated fields inside of this field space, and therefore you need to either change your application or change the max field setting inside of Legion config in order to rebuild the runtime with the proper number of maximum fields. So it's always possible that this allocate index method can fail, but in most cases it will succeed and return to you a new index in which it is safe to allocate a particular field inside of one of these field masks. Okay, let's actually see now how once we've used this allocate index, let me show you another important method here that's associated with this. You saw we called allocate index in this allocate field method, and then we stored some information in this fields data structure to actually create or store this internal metadata. Let me jump back here to regiontree.h and let's look at some of these other methods that we have on field space nodes, and we're going to go look at one of them in particular. Okay, so inside a field space node, we have a whole bunch of different methods. You can see we have things for allocating and freeing fields. By the way, freeing fields, usually what we do is we don't always throw away the metadata for a field right away, but what we do is we free up its index right away. That's the important thing that we have to do. We have things for like getting the field sizes. We have things like getting all the fields and so forth, and getting field sets and so forth. Probably the most important method in here is actually, let's find the one that I am looking for here. Here we go. This is the one I'm looking for. Get field mask from a set of field IDs. So this method right here is going to be the one that we probably call the most frequently on field on field space nodes. And what we're going to do is what we're going to see is that what this method is going to do is going to take a set of field IDs and translate them into a field mask. Now, this data structure here should actually look pretty familiar to you guys. And you know, the place that's going to come from is pretty much every single one of our tasks when they get launched. They declare their set of region requirements that name, you know, which regions they're going to access. What incorporated in those region requirements is a STL set of field IDs saying which fields that region requirement is going to be requesting on that particular region. So what you can imagine is that we're going to end up calling this get field mask call on these set of field IDs that get passed in from region requirements in order to generate a more compact field mask representation of this field set for when we go to do region tree traversals. And what's going to allow us to do is effectively track these field masks are going to allow us to track the active set of fields whenever we're doing traversals based on, you know, these STL set on what was initially passed in as STL sets of fields. We're going to represent them much more compactly with field masks, and it's going to make our traversals significantly more efficient than having to do operations on STL sets. So this get field mask method will be called, you know, pretty much at the beginning of every one of our traversals in order to convert these sets of fields into field mask representation and do our traversals. Let's actually look at this get field mask just so you can see how it works. It's going to be pretty straightforward. Jumping into region tree.cc here. Okay, I'm searching for get field mask. Okay, what you see here is we get in a set of STL field IDs. First thing we're going to do is we're going to claim the lock on this field space node so we can look at this field data structure. Let's see. This field data structure here in read-only mode without anyone mutating it at the same time. But of course, we can have multiple people calling this to create in read-only mode at the same time. What we're going to do is we're going to build a field mask object in which each of the bits inside of this, for each of these field IDs, we're going to set the corresponding index bits inside of this field mask corresponding to those field IDs. So what we do is we iterate over this set of, I intentionally call these privileged fields here because these are most likely privileged fields being passed in from a region requirement. And so what we're going to do is we're going to iterate over this STL set, and we're going to look at all of them. The first thing we're going to do is we're going to look up the field ID inside of this set of fields. And we should always be able to find an entry for this for the metadata for this particular field ID. There's actually some checking that goes on earlier in the runtime that actually checks that all these field IDs are a member of this particular field space, so we don't need to check it again here. So we should always be able to find this metadata, and we should always be able to find an entry in this field data structure for this particular field ID. And then what we do is we go ahead and we set the bit corresponding to the index in which this field ID was allocated. So this field ID, we gave it an index, and we call it allocate index. What we do is we set that corresponding bit in our resulting field mask. And then once we're done, we can go ahead and return the field mask that we just created. And so just to give you an example of this getting called here, to actually be able to find a mask call pretty early on up here. Actually zoom up here a little bit. You can see there's a whole bunch of them up here at the top of the file. And this is going to be intentional because effectively what we want to do is we want to be able to get field masks at the beginning of our region tree traversals, and then we don't want to have to look at the STL sets ever again. We can do everything with existing field masks. So yeah, here's a good example. You can see this is a call to perform dependence analysis. We're going to get in. We're actually going to look at this in some more detail probably a little bit later. But what we're going to see is we're going to get in some information. One of the things that we get in is a region requirement, saying which region requirement we're doing our analysis for. And here we are calling get field mask with the privilege fields from that region requirement in order to generate a set of fields that represent the fields that are going to be accessed by this particular operation that we're going to be tracking. And so what you're going to see is that these field masks play a huge part in the traversal of region tree objects. And one of the main reasons for this is that effectively, the way we're going to use these field masks is that when we go to do traversals, we don't want to be doing traversals on individual fields serially. We don't want to have to do things for the first field and then do things for the second field and so forth. That would actually be very, very slow. Instead, the way to think about this is that we're actually going to do the traversal one time with all of the fields at the same time. What we'll do is whenever there's divergence across the fields, possibly with different fields, taking different paths in the traversal, what we'll do is we'll be able to scope off fields inside of these field masks and build, subsets of the field masks for doing traversals for some of the fields and then coming back and doing, say, the other path with the opposite set of fields turned on. And you're going to see this is going to make our region tree traversals much more efficient. We're going to be able to effectively be doing lots of traversals in parallel for different fields, all at the same time. And these field masks are really what's going to facilitate being able to do these kinds of operations. Okay. Let's see here. I've got about 15 minutes left here, so I'm trying to think about whether I actually want to start logical dependence analysis or whether I want to talk about one of the other details of how of some of the structure of the region tree. I think what I'll do today is I'll actually talk a little bit of detail about how we actually send information about different nodes to remote region or remote runtime instances on other nodes. And we'll start the logical dependence analysis next time. So let's actually look in a little bit of detail about how, say, that we package up things such as region tree nodes and field space nodes and so forth and send them to remote nodes. We're actually going to see, this will actually be good because I'll actually show you some examples of the serializer and deserializer objects that I mentioned earlier today. Okay, let's actually jump back to regiontree.cc here. Let's actually see how we send a field space node since we've been looking at field space nodes. Let's see how we send it to a remote node. So if I search for a field space node, send node, what you can see is we have a method here for actually sending field spaces to what we call these address spaces, but these are really just remote nodes. So it's just some Legion runtime object on a remote node. So this is a target address space that we're going to be sending it to. And so what we're going to want to do is we're actually going to want to package up this particular send node, or what we're going to do is want to package up this particular field space node to actually send it to the remote node. So the first thing we're going to do is we're going to want to grab the lock in order to check to make sure so that we can access our data structures safely. The first thing that we do is we check to see whether or not we've actually already sent this node to this particular remote target. Let me show you these creation sets and deletion sets. You're going to see they look very familiar. So if we look at regiontree.h, and I search for class field space node, what you see here is that we have two different data structures here, one called creation set and one called destruction set. And you see these are instances of node sets. These node sets are actually backed, in most cases, with a node mask object, which is just a variation on those bitmask objects that we looked at earlier today. There's a little bit of complication because node sets actually have another level of indirection for storing very sparse sets, which are not dense bitmasks. But I'm not going to go into that today. But effectively, the way you can think about this is that this is just a set of tracking which nodes know about this particular field space. So every one of the Legion runtimes, for every one of its objects in these region trees, you're going to see they all have one of these creation sets and one of these destruction sets. And effectively, what they do is they keep track of, from the perspective of this particular Legion runtime, which of the other runtimes in the system have I sent this particular field space to. And what this allows us to do is make sure we don't have to do duplicate sends. If we know we've already sent a field space object to another remote node, we know we don't need to send it there again. So that's tracked in the creation set. Where have we known that that a runtime exists that has been notified of the creation of this field space? And then we have a similar set for notifying things like destruction of this particular field space. And what you see is if I actually search for creation space or creation set and destruction set, we're going to have these on pretty much every single type of node inside the region tree object. So you can see we have one here on, I believe this is region tree nodes. Yeah, these are on every single region tree node. We have one of these things. On every type of index tree node, we have one of these things, and on every field space, we have one of these. Space. Yes, this is field space node. On every one of these field spaces, we have one of these creation destruction sets. And so what they do is they effectively just allow us to track where we sent information about the structure of our region tree to different nodes inside of the system. So if I come back to regiontree.cc here, I come back to, actually I want field space node, send node. You can see here one of the first things that we do is we check to see that the target is not in our set of creation set, which effectively means that we know that we haven't sent this particular field space to this target address before. If we have, then we know we're already done. You can see we can actually skip out of the rest of the call, and we're actually already done. But if we haven't sent it before, then we do have to send it. Now, one important detail is that these creation sets actually are incomplete information. They only have information relative to the particular node on which it exists. So it's possible that this field space could actually have already been sent to the target by another node inside the system, but we don't have a way of knowing that. And so this is one of the reasons that the run we looked at earlier. We know that node creation for all of these index space trees and field space trees and field space and region tree nodes and field space nodes all support duplicate allocation. And that's just because we know that we can get multiple requests saying to create this node coming from different other remote nodes. And therefore, this is why this is just a property of distributed systems with incomplete information, is that we can sometimes get duplicate sends of the same information to the same place. But importantly, they should all contain the same information, which we make sure that is always true. So we can always just ignore duplicate creation requests. Okay, if we've decided we need to send the node info, here's one of the important things that we do. What we do is we create one of these serializer objects. So these serializer objects just provide a way of storing a buffer of packed bits for packing up all of the state inside of an object. So these serializer objects have pretty much a single method on them. It's called serialize. And serialize is a template method. And what it does is it knows how to pack up the bits for particular types and serialize them into the bits for these values into the buffer. So you can see it's templated. In some cases, I've actually put the explicit type on there. But in many cases, you actually don't need to do that, just because C++ is strong enough to figure out to do the type inference for you and figure out the right way to package up these values into the buffer. And so what you see that we're doing here is we're packaging up all of the metadata necessary to create this field space node on a remote node. So we're packaging up the field space handle. We're packaging up some of the semantic information. Importantly, one of the things that we're packaging up, let's see, where's the most important thing in here? I guess this is semantic info. I'm looking for where we actually send. Yes. Okay. So what we do is we actually send the field space allocations separately. So what you see is we package up some of the info here for actually sending this field space object. And then we actually tell the runtime to send the field space node to the remote node, which will actually cause this field space object to be created on that remote node. And then one of the things that we do is we also iterate over all of our field space, our actual fields inside of our field space. So this is the fields data structure, our map from field IDs to field infos. And what we do is, as long as these fields haven't been destroyed, we actually go ahead and tell that remote node to actually allocate those fields on that particular remote node. This is one of these cases where we mentioned earlier that the message manager objects inside of the high-level runtime actually maintain some ordering on messages sent to this from one node to another node. And so this is important because we just sent a message saying to create the field space node, and now we're sending messages to actually allocate the fields on this remote node to give them their own separate indexes on that remote node. And so we want to guarantee that these messages actually get delivered in order. If they don't get delivered out of order, it's possible that you could actually see these field allocation messages come before this field space node message that the runtime is sending. And what could happen there is actually, it would be very bad if they happened out of order. So it's very good that our message manager objects maintain an ordered queue between pairs of nodes to guarantee that these messages will arrive in the order that they were sent. And therefore, we know that the field space node object on the remote node will actually already exist there. So what you'll see is that most of these message sending operations just take a target runtime object or target address space where you're actually sending this message, and then a serializer saying, this is the buffer of all the bits that I want to send in this particular message. And so once we've done all that, we can update our creation set to say that, okay, we know that we've sent the information for this field space to that particular remote node, and therefore we won't need to send it ever again. On the reverse side, we actually have these handle node creation calls. So you see this is a static method on the field space node. It's very nice. Effectively, what happens is this goes through the message managers, and the message managers have handlers, which actually will end up invoking this field space node handle node creation call. And what ends up happening here is that we actually have this is one of these cases where we're given a deserializer object for actually deserializing the bytes in the buffer that we packed up here inside of this serializer object. And so what you see here is that what we do is we go through and actually deserialize things in the exact same order. So here's our field space handle. The first thing that we packed inside of this serializer object was this handle saying this is the field space handle for this particular field space. What we do is we unpack things in exactly the same order. So we declare a field space handle, and then we can unpack the result using this deserialize method. This is also a templated method that knows how to unpack all of the bits and assign them into this field space handle. We can unpack a bunch of our semantic information. And then what we do is we eventually will end up calling, after we've actually made this object, this handle node creation, we will actually end up creating this object. So here's where we call create node on side of our, this is a context, so this is the region tree forest object that gets passed in for this particular runtime, and we can call create node with a handle, and then we get back a new field space node object for us to use. And of course, we looked at create node a few times ago for seeing how field space nodes were created. Okay, and so then the rule is you just have to unpack things in the same order that you pack them up in. In order to help, this can be kind of a perilous part of the runtime is packing and unpacking these data structures, because you can actually, if you do things in the wrong order, there's no type system to really help you out here. We do have a little bit of checking here to help us out performing these checks. You see that we have these res checks, and then down here we also have the corresponding res check. Effectively, what these allow you to do is to assign scopes to these serializer objects to say, in a res check, everything that gets serialized inside of this, while this res check is in scope, will effectively get added up and counted to the particular serializer. And so what this allows us to do is to actually track the number of bytes that have been allocated inside of this effectively res check context. And then what we do is in the res check here, we declare we put a res check object on here, and that checks that the number of bytes that are unpacked is exactly the same as the number that were packed in this particular context. And importantly, you can actually nest these res check and res check objects. So for example, if this packing process, traversed, say, part of the region tree data structure, as we'll probably see in some later cases, you can actually have nested res checks, which allow you to check that all the things that were the packing and unpacking was properly scoped, and that the number of bytes packed and unpacked in each of the different scopes ended up being identical. And so that actually gives you a little bit more powerful way of checking that you're packing and unpacking all of these objects correctly. But for the most part, we try to keep notice that this code is actually close to each other in physical space in the file. So it's very easy to, check that these two pieces of code are effectively doing the same thing, packing and unpacking. And this is true of pretty much all of our packing and unpacking calls, as they all tend to be right next to each other in the actual source code, and they're very easy to check that they're actually doing the same thing. Okay, I didn't talk about how the send node or where the send node call was coming from. We'll probably actually look at that in a little bit of detail later. What you'll see is that they're actually send node calls on a bunch of different types of objects inside of the region tree forest here. So we have them on region nodes, we have them on partition nodes, we have them on index space nodes, we have them on index part nodes, and then we're back to field space nodes. So pretty much every single kind of our region tree objects, whether they're field spaces, index spaces, or region nodes, can all support the send node method, which allows us to actually send the structure of these nodes to remote nodes inside of our system, and that's going to allow us to, be able to track these region tree structures across multiple different nodes. And we'll probably look at how send node gets called a little bit later on in our analysis. Okay, so I'm pretty much out of time for today. Next time, what I'm going to do is I'm actually going to get started on how we do logical dependence analysis. Now that we know how we create field masks and what field masks are, I think we're in good place to start looking at how analysis is performed. And so we'll definitely be starting that next time. Okay, unless anyone has any questions, I think we're done for today. No questions? All right, I say we're done.